Bismillahirrahmanirrahim. Rabbi shrah li sadri wa yassir li amri wahlul 'uqdatam min lisani yafqahu qawli. Assalamu alaikum. Today we will do section 1.6 significant figures from the book Physics for Scientists and Engineers with Modern Physics by Serway and Jewett, 10th edition. When certain quantities are measured, the measured values are known only to within the limit of the experimental uncertainty. The value of this uncertainty can depend on various factors such as the quality of the apparatus, the skill of the experimenter, and the number of measurements performed. The number of significant figures in a measurement can be used to express something about the uncertainty. The number of significant figures is related to the number of numerical digits used to express the measurement, as we discussed below. As an example of significant figures, suppose we are asked to measure the radius of a Blu-ray disc using a meter stick as a measuring instrument. Let us assume the accuracy to which we can measure the radius of the disc is plus minus 0.1 centimeter. Because of the uncertainty of plus minus 0.1 centimeter, if the radius is measured to be 6.0 centimeter, we can claim only that its radius lies somewhere between 5.9 centimeter and 6.1 centimeter. In this case, we say that the measured value of 6.0 has two significant figures. Note that the significant figures include the first estimated digit. Therefore, we would write the radius as 6.0 plus minus 0.1 centimeter. 0.0 plus minus 0.1 centimeter means that the value lies somewhere between 5.9 centimeter and 6.1 centimeter. Zeros may or may not be significant figures. Those used to position the decimal point in such number as 0.03 and 0.0075 are not significant. Therefore, there are 1 and 2 significant figures respectively in these two values. When the 0 come after other digits, however, there is a possibility of misinterpretation. For example, suppose the mass of an object is given as 1500 gram. This value is ambiguous because we do not know whether the last two zeros are being used to locate the decimal point or whether they represent significant figures in the measurement. To remove this ambiguity, it is common to use scientific notation to indicate the number of significant figures. In this case, we would express mass as 1.5 into 10 raised to the power 3 gram if there are two significant figures in the measured value, 1.50 into 10 raised to the power 3 gram if there are three significant figures, and 1.500 into 10 raised to the power 3 gram if there are four. The same rule holds for number less than 1, so 2.3 into 10 raised to the power minus 4 has two significant figures and therefore could be written 0.00023, and 2.30 into 10 raised to the power minus 4 has three significant figures and therefore written as 0.000230. The 0 after the decimal is not a significant figure, as 0.03 is just one significant figure. 0.0075 has two significant figures. If we write in scientific notation, things become a lot more clearer. For example, 1.5 into 10 raised to the power 3 gram is two significant figure. 1.50 into 10 raised to the power 3 gram is three significant figures, and 1.500 into 10 raised to the power 3 gram is four significant figures. Similarly, for values less than 1, 2.3 into 10 raised to the power minus 4 is two significant figures, and 2.30 into 10 raised to the power minus 4 is three significant figures. We need to be clear that which zeros are counted as significant figures and which zeros are not counted as significant. In problem solving, we often combine quantities mathematically through multiplication, division, addition, subtraction, and so forth. When doing so, you must make sure that the result has the appropriate number of significant figures. A good rule of thumb to use in determining the number of significant figures that can be claimed in a multiplication or division is as follows. When multiplying several quantities, the number of significant figures in the final answer is same as the number of significant figures in a quantity having the smallest number of significant figures. The same rule applies to division. Let's apply this rule to find the area of the blue ray disk whose radius we measured above, using the equation for the area of a circle. A is equal to pi r square, where A is area and r is radius. The radius is equal to 6.0 centimeter. Therefore, area is equal to pi times 6.0 centimeter square. And the answer is 1.1 into 10 raised to the power 2 centimeter square. If you perform this calculation on your calculator, you will likely see 113.0973355. It should be clear that you don't want to keep all of these digits, but you might be tempted to report the result of 113 centimeter square. This result is not justified because it has 3 significant figures, whereas the radius only has 2. Therefore, we must report the result with only 2 significant figures as shown above. For addition and subtraction, you must consider the number of decimal places when you are determining how many significant figures to report. When numbers are added or subtracted, the number of decimal places in the result should equal the smallest number of decimal places of any term in the sum or difference. As an example of this rule, consider the sum 23.2 plus 5.174 is equal to 28.4. Notice that we do not report the answer as 28.374 because the lowest number of decimal place is 1 for 23.2. Therefore, our answer must have only one decimal place. 23.2 has one decimal place, 5.174 is 3 decimal place. Our answer should have only one decimal place, that is 28.4. The rule for addition and subtraction can often result in answers that have different number of significant figures than the quantities with which you start. For example, consider these operations that satisfy the rule. Let's consider a case of addition. 1.0001 plus 0.0003 is equal to 1.0004. Let's consider a case of subtraction. 1.002 minus 0.998 is equal to 0.004. Let's consider the numbers. 1.0001. It has 5 significant figures. We add it to 0.0003. It has only one significant figure. The answer is 1.0004. It has 5 significant figures. Let's consider the numbers we considered for subtraction. 1.002. It has 4 significant figures. Minus 0.998. It has 3 significant figures. The answer 0.004 has 1 significant figure. In the first example, the result has 5 significant figures, even though one of the terms 0.0003 has only one significant figure. Similarly, the second calculation, the result has only one significant figure, even though the numbers being subtracted have 4 and 3 respectively. In this book, most of numerical examples and end of chapter problems will yield answers having 3 significant figures. When carrying out estimation calculation, we shall typically work with a single significant figure. Pitfall prevention. Read carefully. Notice that the rule for addition and subtraction is different from that of multiplication and division. For addition and subtraction, the important consideration is the number of decimal places, not the number of significant figures. If the number of significant figures in the result of the calculation must be reduced, there is a general rule for rounding numbers. The last digit retained is increased by 1 if the last digit dropped is greater than 5. For example, 1.346 becomes 1.35. If the last digit dropped is less than 5, the last digit remains as it is. For example, 1.343 becomes 1.34. If the last digit dropped is equal to 5, the remaining digit should be rounded to the nearest even number. This rule helps avoid accumulation of errors in long arithmetic processes. The number 1.346, the last digit is greater than 5, therefore we will round it to 1.35. If we consider the number 1.343, the last digit is less than 5, therefore we will round it off to 1.34. If we have the number 1.345, we will round it to the nearest even number, that is 1.34. If we have a number 1.355, we'll round it to the nearest even number, that is 1.36. In a long calculation involving multiple steps, it is important to delay rounding of numbers until you have the final result in order to avoid error accumulation. Wait until you are ready to copy the final answer from your calculator before rounding to the correct number of significant figures. In this book, we display numerical values rounded off to 2 or 3 significant figures. This occasionally makes some mathematical manipulation look odd or incorrect. For instance, looking ahead to example 3.5 on page 62, you will see the operation minus 17.7 km plus 34.6 km is equal to 17.0 km. This looks like an incorrect subtraction, but that is only because we have rounded the numbers 17.7 km and 34.6 km for display. If all the digits in these two intermediate numbers are retained and rounding is only performed on the final number, the correct 3-digit result of 17.0 km is obtained. If we subtract 34.6 km minus 17.7 km, we get the answer of 16.9 km. That is only because we are using the rounded numbers of 17.7 km and 34.6 km. If we had kept the original number, the final answer would have been 17.0 km. Example 1.6, installing a carpet. A carpet is to be installed in a rectangular room whose length is measured to be 12.71 meter and whose width is measured to be 3.46 meter. Find the area of the room. If you multiply 12.71 meter by 3.46 meter on your calculator, you will see an answer of 43.9766 meters square. How many of these numbers should you claim? Our rule of thumb for multiplication tells us that you can claim only the number of significant figures in your answer as are present in a measured quantity having the lowest number of significant figures. In this example, the lowest number of significant figure is 3 in 3.46 meters, so we should express our final answer as 44.0 meters square. May Allah bless us all. Thank you for watching. Allah Hafiz.